Finally, we have our very last section of Math 150. It is 10.3 on measures of dispersion. So last time, 10.2, we had measures of central tendency, which given some sample of data, we were trying to find the approximate midpoint of the data, right? That's what mean, median, mode did. Measures of dispersion are measures of how widely dispersed your data actually is. So there's more to data than just identifying the midpoint. For example, here's two different samples. Sample number 1 is just 2, 2, 3, 3, 4, 4. Sample number 2 is 2, 3, 3, 3, 3, 4. And both of them, if you were to check the mean of both of them and the median of both of them, you would get same mean, which is 3. Right, and what I've indicated here is I've drawn little histograms of my data. Right, so I've got the number 2 appearing twice, the number 3 appearing twice, the number 4 appearing twice, and over here the number 2 appearing once, number 3 appearing 4 times, number 4 appearing once. So I've drawn histograms of the data, and if you were to look at the mean of both of these samples, you would get the same mean. They both have the same mean, 3, but in terms of the distribution of the data, it's very different. Right? This is sort of uniformly distributed, meanwhile this is more bell-shaped. And this is because they have different what's called variances, or different standard deviations. Right? So there's a different distribution here. And the question is, how can we measure this difference? How do we measure, sorry about the handwriting, it's low on the board, how do we measure the difference in distribution? And we're going to introduce a number called the variance for a given sample, or the standard distribution. They're both very closely related to each other. And a smaller variance, or a smaller standard distribution, would match something more like sample number 2, where smaller variance, smaller standard distribution tells you that the data is more centrally clumped. It tends to clump around the mean, while a larger variance, or a larger standard deviation, tells you that your data is much more spread out. It's more distributed away from the actual mean. So I guess the next thing to do is introduce these values. How do we compute variance and standard deviation? So here's the formulas. If I have n sample measurements and my data consists of n numbers x1 out to xn, we compute the mean, we get x bar the mean, then the sample variance, which I'll call s squared, is given by the following formula. And this is given in summation notation, but what this says is you take all of the elements in here, all the elements in your sample, so x1, you take x1, you subtract off the mean, and then you square it. Then you take x2, subtract off the mean, and you square it. You take x3, subtract off the mean and square it, add them all together, and then divide by n minus 1, which is 1 less than the total number of elements in your sample. That's the variance. And as we discussed already, smaller variance means that your data is more bell-shaped, it's more clumped around the mean. Larger variance means your data is more dispersed, more spread out. And the sample standard deviation, s, is just the square root of the variance. So it's the square root of s squared, square root of this expression here. And these formulas look a little bit scary, but my job is to convince you that it's not. So let's just jump straight into some examples. So how about we start off with the two samples we started this lecture with. So my first sample is 2, 2, 3, 3, 4, 4. And we've already agreed the mean, x bar, you can compute it. It's 2 plus 2 plus 3 plus 3 plus 4 plus 4 over 6. Compute it. I promise you'll get 3. And yeah, now we're going to compute the variance. So s squared. So what do? Going back to that formula said take every element, subtract off the mean, and square it. Right? So I've got 2 minus 3 squared plus 2 minus 3 squared plus 3 minus 3 squared plus 3 minus 3 squared, running out of space, plus 4 minus 3 squared plus 4 minus 3 squared. And then you divide by not n, you divide by n minus 1. So n is 6, I divide by 5. Alright, so this actually looks pretty simple. This is minus 1 squared, which is 1. So I've got 1 plus 0 plus 0. 4 minus 3 squared is 1 squared plus 1 over 5. So that's 4/5 or 0.8. So there's the variance. How do you get standard deviation? S? Well, it's just the square root of s squared, of the variance. So it's just the square root of 4/5, which is 2 over root 5, or if you want an approximation, that's approximately 0.89. And you'll see problems like this for homework that just give you some data. They say, what's the mean? What's the standard deviation? Here's the way to compute it. Let's do sample number 2. We agreed that this sample sort of was more bell-shaped. The data was more centrally clumped. So we're going to expect to find a smaller standard deviation here. Once again, find the mean. The mean is 3. And yeah, we'll just go ahead and compute the variance. So do the same thing. Take each element, subtract off the mean, and square it, and add them all together. So 2 minus 3 squared plus 3 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 minus 3 squared plus 4 minus 3 squared, all over n minus 1, which is, there's 6 elements, so n minus 1 is 5. This is minus 1 squared, which is 1, plus 0, plus 0, plus 0, plus 0, plus 1. All over 5. So that is 2/5, or 0.4. So I have a smaller variance. I'm expecting to find a smaller standard deviation. S is the square root of 2/5. Which, plugging this into a calculator, I got about, I'll put an approximation, 0.63. Alright, so this is what this is doing for us. The standard deviation is measuring how widely dispersed your data is versus how centrally clumped it is against the mean. And a smaller standard deviation tells you that your data is more bell-shaped, more clumped up in the middle. That's really all there is to it. Let's just do one more example, I guess. Alright, so here's the question. Find the mean and standard deviation for the following set of data. The data is 4, 2, 3, 5, 3, 1, 6, 4, 2, and 3. If I was going to find the median, I would have to order this, right? It would have to be an ordered list, so I'd have to reorder this in terms of increasing size. But to find the mean, I don't have to worry about that. So what's the mean going to be? The mean is just the sum of all of the numbers, 4 plus 2 plus 3 plus 5 plus 3 plus 1 plus 6 plus 4 plus 2 plus 3, all over the total number of elements in this set, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all over 10. So now we just have to add these, 6, 9, 14, 17, 18, 24, 28, 30, 33. 33 over 10, or 3.3. Alright, so there's the first part done, mean 3.3. Now, we want to find the standard deviation. So the first thing we'll do is we'll compute the variance and then square root it. So the variance, how do we do that? Well, we take each element in the set, 4, and we subtract off the mean, 4 minus 3.3, and we square it. And then add to it add to it doing this for every element. So then we've got 2 minus 3.3 squared plus 3 minus 3.3 squared plus 5 minus 3.3 squared plus 3 minus 3.3 squared. How far am I? I'm up to 1 plus 1 minus 3.3 squared plus 6 minus 3.3 squared plus 4 minus 3.3 squared plus 2 minus 3.3 squared plus 3 minus 3.3 squared. And what do we divide by? We divide by n minus 1. In the mean, we already found there were 10 numbers in this list, so n minus 1 is 9. And you can simplify this quite a bit. You can group like terms together and whatnot before you plug this into a calculator if you want, or you could just plug this straight into a calculator. I get that this is about it's about 20.1 over 9, which is about 2.233, and we'll just go to 3 decimal places. Alright, so our standard deviation is the square root of this, square root of 2.233, and that is about 1.494. So that's all there is to it. This is how you find standard deviation. Again, the formula looked a little bit scary in summation notation, but hopefully you'll see that going through examples and just applying it, it's a fairly straightforward formula, right? Take every element, subtract off the mean, square it, and add them all together, and then divide by n minus 1. Now this section also does standard deviation for grouped data. We're only doing ungrouped data here. For the group data, if you want to read through it, that's fine. But I think we'll just stop here. I won't include any of the group data on any homework or quizzes or anything or exams. So we'll cut this section short and just look at ungrouped data. All right, thanks.